Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1. Bromine and mercury are the only elements that are liquids at room temperature. All other elements in the periodic group that contains mercury are solids. Why are mercury and bromine not in the same group? Okay. So this is just because when you have different elements that are grouped together in the same group, they don't necessarily need to have the same physical properties. So the reason why they are in like that numerical order that they're in is just because of their number of protons that are in the element. And also it helps us to visualize kind of all of their valence electrons. And when you go down a period, how they all kind of have the same number of valence electrons, but the atomic radius just gets bigger and bigger. So grouping them just because they have the same physical properties isn't really that ideal. So that's why bromine and mercury aren't in the same group. So let's see what the junior tutor said. Element groups in the periodic table are arranged in such a way that they have a similar number of valence electrons, similar patterns in forming compounds, and similar chemical properties. Remember that elements within the same group do not necessarily have the same physical properties. Remember also that a compound's characteristics are independent of its components' characteristics. Yep, so that's a good answer. So this solution is correct. Okay, so question number 2. Calculations using STP and SATP use the same, different values of R. Choose one phrase to make the statement correct and defend your choice. Okay, so STP. So this stands for standard, temperature, and pressure. So for STP, the temperature is 0 degrees Celsius or 273 Kelvin. And in the case of the pressure, it is 1 atm or 101.325 kilopascals. But for SATP, this is standard, ambient temperature and pressure. So under these values, the temperature is 25 degrees Celsius, or 298 Kelvin. And the pressure is around 100 kilopascals. So they actually both use the same value of R. When we perform calculations. Junior Tutor said that STP means standard temperature and pressure, while SATP means standard ambient temperature and pressure. Although in both cases the standard values of pressure and temperature are different, both may use the same R values since the conversion of one unit to another is not a complicated method. Therefore, to answer the problem, calculations using STP and SATP use the same values of R. Yep, so the solution is correct. Okay, so question 3. What is the electron configuration for titanium 2+? So for electron configuration questions, we need to follow the following steps. One is to divide your periodic table into the different orbitals. So either S, E, D, and F. So I can show what that looks like. Periodic table. So it's actually pretty simple to divide it. You can see the two left columns and helium are light blue, and they correspond to the S block. The green kind of rectangle here is the P block, and the middle transition metals is the D block. And finally, the bottom two rows are the lactanides and actinides, and it is the F block. So after we divide the periodic table into these orbitals, then starting from hydrogen, you kind of move from left to right down the periodic table, move left to right, and then you want to write your row number, then the block letter. Once you get to the D orbital, it becomes the row number -1. And once you get to the F block, you write the row number -2. Okay, so this will make more sense if we just do our example first. So for the question, it's asking for titanium 2+, I believe. Yep. So notice that the titanium has a +2 charge, so this means it lost 2 electrons. So to help us write down its electron configuration, we first need to write down the ground state electron configuration for titanium. So this is when it's just neutral, no electrons have been removed. And so let's try to find it on the periodic table. You can see it's right here, atomic number 22. So starting from hydrogen, if we move left to right, when we write the row number, it's row 1. The block letter is S. And then to show the number of electrons up to helium, it is 1s2. Then we can do the same thing for row 2, block S, and then up to the beryllium, which is here, it'll be 2s2. And then moving over to the P block, it is 2p6. So now we're at neon. And then over to the next row, it's 3s2, and then 3p6. And then moving down, it would be 4s2, and then 3d2. But once we get to the transition metals, it's good practice to write the block letter in order of increasing energy. So I'm going to write the D block first. So 3D up to titanium is 2. And then the 4s orbital, which is lower in energy, or higher in energy, sorry, is 4s2. So I kind of just switched the two around. So you'll notice that when it comes to the transition metals, the D block and the S block tend to switch places. Okay, so this is the electron configuration for ground state titanium. If we wanted to write this in the shorthand configuration, all you need to do is find the noble gas that comes before titanium. So in this case, it's argon. So I'm going to write argon in square brackets. And then we just kind of continue on writing the rest of the electron configuration. So it's argon, 3d2, 4s2. Okay, so now for the question, we want to look at titanium when it has 2 electrons removed. So basically, when 2 electrons are removed, we're going to take the 2 electrons from the s orbital. So it becomes argon 3d2. So this is because partially filled, or I'll just say the filled d orbitals are more stable. Okay, so let's see what the junior tutor said. Okay, so to answer this, we need to first determine the electron configuration of the elemental titanium. By inspecting the periodic table, titanium belongs to period 4, group 4, and has an atomic number equal to 22. The atomic number tells us that the neutral form of titanium must account for a total of 22 electrons. Therefore, the configuration, I think they mean to say titanium, in elemental form would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Now we have the titanium ion. The 2 plus here means that titanium loses think they mean 2 electrons from its outermost shell. In this case, the 2 electrons lost would come from the 4th energy shell, 2 from the 4s orbital. This means that the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. Yep, so this solution is correct. And then I'll just put in brackets to fix the typos. Titanium 2 plus means that titanium loses 2 electrons. Okay, so on to question number 4. Draw the ether formed when ethyl alcohol is heated in the presence of concentrated sulfuric acid. Okay, so ethyl alcohol is also referred to as ethanol. So because it has the prefix eth, that means it has 2 carbons. And the fact that it ends in -ol means that it also contains an alcohol group. So this will help us answer the question. So when we have ethyl alcohol, I'll draw out the structure. So again, it is 2 carbons. There is an alcohol group. And then the rest of the carbons just have hydrogens. Okay, so this is 1 molecule of ethanol. But when it is in the presence of concentrated sulfuric acid, then it will form an ether. And the way that it does that is that it forms it with another molecule of ethanol. So I'm just going to draw second ethanol beside it. Okay, so H2SO4 is a strong acid, and under heat, water would be removed, and then you form the following ether. So ether is when you have an oxygen in between 2 carbon atoms. And the name of this ether is diethyl ether. And then we also formed water in this reaction as well. Okay, so let's see what the junior tutor said. When 2 equivalents of ethyl alcohol or ethanol are treated with concentrated sulfuric acid in the presence of heat, the bond between the R group and the OH group is broken down, forming an ether, particularly diethyl ether. Yep. So the solution is correct. Okay, so question number 5. Sodium bicarbonate reacts with acetic acid and causes a chemical reaction. What are the end products of this reaction aside from water? Okay, so first let's write down our reactants. We have sodium bicarbonate. So the chemical structure of sodium bicarbonate is sodium, obviously, and bicarbonate ion. So this reacts with acetic acid. So the formula for acetic acid, CH3, COOH. And then when they react, a double displacement reaction would first occur. So pretty much the sodium switches places with the hydrogen. And then we are left with sodium acetate plus H2CO3. However, this molecule is unstable and it can be broken down further into water and carbon dioxide. So let me just rewrite the reaction down here. Okay, so this product stays the same. But this breaks down into H2O plus CO2. So the end products of this reaction, aside from water, is sodium acetate and H2O. I mean CO2. Okay, so let's see what the junior tutor said. Note that the chemical formulas of sodium bicarbonate and acetic acid are NaHCO3 and CH3COOH, respectively. Using double displacement reaction, the chemical reaction can be written as... Yep. However, carbonic acid is highly unstable and can be decomposed into water and carbon dioxide. So they showed how carbonic acid is decomposed. Hence, the chemical reaction is written as sodium acetate plus water plus CO2. Yep, so this solution is correct. Okay, so question number 6. A redox reaction can be easily explained as... So I guess we have to pick one of the options. So let's go over all of them. We have an attraction between opposite charges. So this is also known as ionic bonding. So it's not a redox reaction, since it's when we have opposite charges such as sodium plus Cl minus forms an ionic bond. B, forming a bond by sharing electrons. So this is known as covalent bonding. And it occurs between nonmetals. So examples of covalent bonding would be like hydrogen sharing its electrons with oxygen. And C, transferring electrons between reactants. So C is actually what a redox reaction is. Let me just circle it because that's our answer. We can also just quickly look at the last two options. The breakdown of glucose in cells is glycolysis. And the temporary storage of cellular energy. So this reaction, I think, just might be photosynthesis, since plants store their energies in the form of bonds, and then once their bonds are broken, then that's how they get ATP. Okay, so Junior Tutor said transferring electrons between reactants. So this is a redox reaction. The redox reactions are reactions that involve one species being reduced while another one is being oxidized. Therefore, the oxidation state of the species involved must change. Reduction is a process in which an atom gains an electron and therefore the oxidation number decreases. Oxidation is a process in which an atom loses an electron and therefore the oxidation number increases. So in a sense, the species undergoing oxidation will transfer electrons to the species undergoing reduction. Yep, so this solution is correct. Okay, so question number 7. How many orbitals in an atom can have each of the following designations? A, 5F, B, 4P, C, 5D, D, N equals 2. Okay, so to answer this question, I'm going to find all the different quantum numbers for each of these different orbitals. So starting with 5F, its n quantum number is just equal to 5. And to find our L quantum number, this is from the block letter. So I'm going to write all the different L values up here. So when you have electron in the S block, its L value is 0. For the P block, it's 1. The D block, it's 2. And for the F block, it's 3. Okay, so keeping that table in mind, when we have an electron in the 5F orbital, that means its L value is equal to 3. So because our L value is equal to 3, that means our L value can range from -3 to +3. So I'm just going to write all the different ML values from -3 to +3. Okay, so since we have all these different orbitals. If we count it all out, then therefore there is 7. So 7 orbitals in an atom that has a 5F designation. Okay, so let's do the same thing for B. For the 4p orbital, n is equal to 4, L is equal to 1. So that means our ml value ranges from -1 to +1. So that means there's only 3 orbitals. C, we have 5d. So n is equal to 5, L is equal to 2, and our ml value ranges from -2 to +2. So that is 5 orbitals. And then now let's look at D. When n equals 2, that means that our L value has to be less than 2. So they didn't specify what it is, so I'm just going to say L can either be equal to 0 or 1. So that means our M value, our ML value, is either equal to 0 or it's equal to ML -1, 0 to +1. So in total, there are 4 options. Oh, orbitals. Okay, so let's see what the junior tutor said. The principal quantum number n describes the energy level in which the electron can be found. The angular momentum quantum number L describes the subshell or orbital type in which the electron is located. If the shell of the subshell is not identified, the accepted value of L is based on n. It can have values ranging from 0 to n minus 1. For the S subshell, L equals 0. For the P subshell, L equals 1. For the D, L equals 2. And for the F, L equals 3. Now I'll fix that typo in a bit. So the magnetic quantum number ML describes the orientation of the orbital. It can be determined from the value of L. The accepted values of ML ranges from -L to +L. A. For 5F, L is equal to 3, hence ML equals -3, -2, -1, 0, 1, 2, or 3. So a total of 7 orbitals in an atom can have the given designation. For 4p, L is equal to 1, hence ML is equal to -1, 0, or +1. Therefore, 3 orbitals in an atom can have the given designation. For 5d, L is equal to 2, hence ML is equal to -2, -1, 0, +1, or +2, total of 5. And then for n equals 2, L can either be equal to 0 or 1. So for L equals 0, ML is equal to 0, so total of 1. L equals 1, ML is equal to -1, 0, or +1, total of 3. Therefore, 4 orbitals in an atom can have the given designation. Yep, so the solution is correct. And then I'll just put in brackets for the F subshell, L is equal to 3. Okay, so question number 8. How do you calculate KSP from molar solubility? Okay, so first, let's define molar solubility. So this is the number of moles of solute that can be dissolved per liter of solution before it becomes saturated. So when you have a solution that has a lot of moles of the solute, so more than its molar solubility, that means a solid starts to form and you start to see this precipitate. So precipitate is denoted as PPT, so I'll just put PPT in brackets. Okay, so to calculate KSP from molar solubility, it's just easier if I just show an example. Okay, so let's say we needed to calculate the solubility of the following reaction. So we have aluminum oxide, that's a solid. In solution, it can be separated into its ions, aluminum 3+, aqueous, plus 3 OH minus hydroxide ions. Okay, so everything is balanced, and now I'm going to construct an ice table. So initial, the change, and equilibrium. So when we have a solid, the solid isn't included in the ice table, and we're only interested in the ions in the aqueous solution. So the initial concentration of these ions, since they are products, since they're products, they start off with 0. Since when we have a reactant at the start of the reaction, it doesn't form any product yet, so that's why its initial concentration is always 0. For the change, in the case of aluminum 3+, it will just be plus X. And in the case of the hydroxide ion, since there are 3 moles of hydroxide, it changes by 3x. So at equilibrium, the concentration of aluminum 3+ is equal to X, and for the hydroxide ion, it's equal to 3x. So KSP can be expressed through the concentration of the aluminum ion times the concentration of OH minus to the power of 3, since it has a coefficient of 3 in the balanced equation. So I can also solve for molar solubility by subbing in S as the concentration values. So in the case of the aluminum 3+, I'll just denote it as S. But for the case of the hydroxide, it's going to be 3s, since again there are 3 moles of hydroxide, and this is to the power of 3. Okay, so now that we have this expression, if our molar solubility is given, then we can just solve for KSP. So KSP is just the solubility product constant. Okay, so let's see what the junior tutor said. To consider the dissociation reaction of XAYB shown in equation 1. So here they have an example of a compound that has like compound X and Y, and however many atoms are in the compound are denoted as A and B. And they showed that when this compound dissociates, it forms a number of X ions, which has an oxidation number of B plus B number of Y ions that has an oxidation number of A minus. Okay, so here we have a salt that dissociates into its cation and anion. Equation 2 shows the KSP expression of the above reaction. Okay, so then they show how KSP is equal to the concentration of the ions multiplied together, and then they're to the power of their coefficients. So the molar solubility is related to the concentration of the ions. For example, the molar solubility is related to the concentration of XB plus seen in equation 3. Okay, so they showed it here. In equation 3, A is the stoichiometric coefficient of the ion, and S is the molar solubility of the ion. We can also apply equation 3 to Ya minus, so to get the KSP of the salt, we substitute this molar solubility expressions into equation 2. The result is in equation 4. Yep, so they showed how the coefficient is shown inside the brackets, and it's also raised to the power of that same coefficient value as well. So this can be related to our example, where for the hydroxide ion, we had 3s, also to the power of 3. So this solution is correct. Okay, so question number 9. What is an addition reaction of alkenes? Okay, so addition reaction of alkenes. So this is when unsaturated hydrocarbons that can participate in a number of different addition reactions. So all of these different reactions can take place across their double or triple bonds. But for simplicity, I'll just show an example of an addition reaction across a double bond. So let's say we had an alkene when it reacts with a compound. So let's say compound XY, the double bond gets reduced to a single bond. So I'll just show all the hydrogens that are added. And X and Y are added to the carbons. Move this arrow out of the way. Okay, so I'll just write down some examples of different addition reactions. So different XY values. So this can include hydrogenation, so this is when XY can just be molecular hydrogen. So when you have an alkene reacting with molecular hydrogen and a metal catalyst, then the double bond can just get reduced to a single bond and hydrogens are added. So this is just the addition of hydrogens. You can also have halogenation. So this is when you add a halogen, so like chlorine or fluorine. I'm just going to denote it as X2. Or you can also have kind of like a combination of the two called hydrohalogenation. So this is when we have H and a halogen. So one of the carbons will have the hydrogen and the other one will have either the chlorine, fluorine, or bromine, depending on which halogen you use. It'll just add 1. Okay, so the junior tutor said that alkenes are organic compounds with at least one double bond between carbon atoms. Alkenes may react with other compounds to form a larger compound. This reaction is called the addition reaction. For example, propene will react with hydrogen bromide. Here, the hydrogen in hydrogen bromide will become slightly positive, as bromine will take all over its electrons, making it slightly negative. Since hydrogen is slightly positive, it will get the electrons in the pi bond of the carbon that is formerly in the double bond of propane, or propene, I guess. Markovnikov's rule applies here. That is, hydrogen will attach to the carbon with the highest number of hydrogen atoms. This will cause the double bond to become a single bond only. So they showed how the hydrogen was added to the side that contains more hydrogen atoms. So this is the left side. And then they showed the carbocation that was formed after the double bond was reduced. Now, since one of the carbons with a double bond formerly is now positive, the Br- will then attach to it. So then they showed the bromine coming in to neutralize the positive charge, and then they are left with their product. Yep, so this solution is correct. I'll also just add some snippets of my answer as well. I can say that this includes hydrogenation, so the addition of H2, halogenation, X2, or hydrohalogenation, HX. Okay, so those are all the questions for today's session, and if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description, and also if you enjoyed today's video, you can leave it a like and a comment, and share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.